This is our second video on elevators. So here we have an 80 kilogram person standing on a scale in an elevator. So obviously this is a very realistic scenario. This happens quite a bit. Determine the person's acceleration if the scale reads 800 newtons. Then list the three things the elevator might be doing at that instant. If we were to draw a free body diagram of this, there's the person, and that person has a weight mg, and then the scale is the normal force that holds the person up. Well, what's mg? Mg is 800 because g is 10, so that's 800 newtons. And if the normal force is also 800, well, then the acceleration is 0 meters per second squared. What could be happening at that instant? Either the elevator is at rest, or it's moving upward at a constant velocity, or it's moving downward at a constant velocity. Those are the three options. At any of those times, the bathroom scale on the elevator will read what your weight is. Point 2 here. Determine the person's acceleration when the scale reads 680. And then list the two things that the elevator could be doing. Again, if we draw a free body diagram, mg downward was 800. And now we're told that the scale only reads 680 newtons. What's the net force? The net force is 800 minus 680. So that's 120 newtons, and that needs to equal the mass times the acceleration. That's m right there. So I'm thinking here that that's 120 divided by 80, 1.5 meters per second squared. That's the rate at which that elevator and that person are accelerating. Let's look at the picture here. What are the two things that the elevator could be doing? It could either be moving upward and slowing down, or moving downward and speeding up. Because which way is this acceleration vector pointing? Let's look at the free body diagram that we've done. The acceleration is pointing that way. That's key, because if the acceleration points downward, which it does, if the scale reads 680, the acceleration is directed towards the Earth. End of story. So if the thing is moving upward and accelerating downward, then you see it has to be slowing down. On the other hand, if it's moving downward, that's the direction of the velocity vector. If the velocity vector and the acceleration vector are pointing in the same direction, then it has to be speeding up. One more case. Determine the person's acceleration when the scale reads 1040 newtons, and list the two things the elevator could be doing. So one more time. We're told now that the elevator, the scale that is, reads 1040 newtons, and the weight of the person we know is m times g, so that's 800. What's the net force? The net force is 240. F net equals m times a. So this is 240 newtons, and I'm going to put a direction on that, up. There's a net 240 newtons up, and that's equal to the mass, which is 80, times the acceleration. So I think the acceleration is 3 meters per second squared upward. If the acceleration is 3 meters per second squared upward, what could be happening? Well, if it's moving upward, then it's going faster, 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 because the acceleration points upward. The acceleration and velocity point in the same direction, we have speeding up. If acceleration and velocity point in the opposite direction to each other, then the object must be slowing down.